Good morning. Next topic, Motional Emf from Laurent Force. Consider a straight conducting rod AB of the length small l in a uniform magnetic field V vector, which is the director perpendicularly into the plane of the paper as shown the figure 4.9a. The length of the rod is normal to the magnetic field. Let the rod move with a constant velocity v vector towards the right side. When the rod moves, the free electron present in it also moves with the same velocity v vector in v vector. As a result, the Laurent forces act and free electron is the direction from B to A, and it is given by the relations equations FB vector is equal to minus of small e open the bracket V vector cross B vector close the bracket. Equation number 1. The action of these Laurent forces is to accumulate the free electron at the end A. These accumulations of free electron produce a potential differences across the rod, which is the term established as electric field E vector directed along BA. Due to the electric field E vector, the Coulomb force started acting on the free electron along AB, and it is given by relations equations F E vector is equal to minus of small e and into capital E vector. The magnitude of electric field E vector keeps on increasing as long as accumulations of electron at the end A continues. The force of E vector also increases until the equilibrium is reached. At equilibrium, the magnetic Laurent forces Fb vector and the Coulomb forces Fe vector balance each other and no further accumulation of free electron at the end A take place. That is modulation of Fb vector that is equal to modulation of Fe vector. Fe vector values the modulation of minus of small e V cross B vector that is equal to modulation of small e into capital E vector. Minus e cancelled. Now here Vb sin 90 that is equal to E. Sin 90 is equal to 1, Vb is equal to capital E. The potential differences between two ends of the rod is potential difference V is equal to E into L. The potential difference capital V that is equal to small Vb into L. Thus the Laurent forces on the free electron is responsible to maintain these potential differences and hence produce as a electromagnetic forces EMF is equal BLV. Equations number 4. As this EMF is produced due to the movement of the rod, it is often called as a normal force. In the end A and B, they are connected by the external circuit of total resistance capital R. Then current I is equal to E by R. The values of E is equal to VLV divided by caps R. Flow in it. The direction of the current is found from right hand thumb rule. Thank you. Next, emotional EMF from Faddy's law and energy conservation. Let us consider a rectangular conducting loop of width L in a uniform magnetic field B vector, which is perpendicular to the plane of the loop and it is directed towards. A part of the loop is the magnetic field while the remaining part is outside the field. Show the figure. When the loop is pulled with a constant velocity v vector to the right, the area of the portions of loop within the magnetic field will decreases. Thus, the flux linked with a loop will also decreases. According to Faddy's law, an electric current is induced in the loop which flow in a direction as to the oppose the pull of the loop. Let small x be the length of the loop which is still within the magnetic field. Then it is a area is Lx. The magnetic flux linked with the loops is pi v is equal to area of the integration v vector dot dA vector that is equal Va cos theta. Here theta is equal to 0. Cos 0 is equal to 1. That is equal to BA in the meanings, the BLX, the area of breadth into length. As this magnetic flux decreases due to the movement of the loop, the magnitude of induced EMF is given by E is equal to d phi b divided by dt. That is equal to d by dt into BLX. Here, B and R, L are constants. Therefore, E is equal to BL dx by dt. dx by dt is equal to velocity. E is equal to BLV, where V is equal to dx by dt is the velocity of the loop. This EMF is known as a motional EMF since the produced due to the movement of the loop in the magnetic field. From Laurent Force, it is found that induce the current flow the clockwise direction. If a capital R is the resistance of the loop, then the induced current is given by small I is equal to E by R. I is equal to values of E is equal to BLV divided by R. Next, energy conservation. In order to move the loop with a constant velocity v vector, a constant force that is equal and opposed to the magnetic force must be applied. Therefore, mechanical work is done to move the loop. Then the rate of doing work or power is capital P is equal F vector dot V vector, that is equal Fe cos theta, that is equal Fe. Theta is equal to 0, cos 0 is equal to 1. Now let us find the magnetic force acting on the loop due to the movement is a magnetic field. Let three deflecting forces F1, F2, and F3 vector with acting on the three segment of the loop as shown the figure. The general equations of such a deflecting forces is given by Fd vector is equal to small I L vector cross B vector. The forces F2 vector and F3 vector are equal in the magnitude and opposites in the directions and cancels each other. Therefore, the force F1 vector alone act on the left segment of the loop in the direction shown the figure is given by F1 vector is equal to small I L vector cos B vector. F is equal to I L B sin theta, equations number 1. Here theta is angle between B vector and the length vector L vector for the left segment and the 90 degree. F1 is equal to IL B sin 90 is equal to ILB since sin 90 is equal to 1. The applied forces F vector must be the equal to the F1 vector in order to just move the loop with a constant velocity V vector. Here F vector is equal to minus of F1 vector since the F1 and F2 are opposite direction. Considering only the magnitude, capital F is equal to capital F1, that is equal IL capital B. Here the values of substitutions. F is equal values of F1 BLV divided by capital R into LB. F is equal to B square L square V divided by R. These equations are rate at the which is a mechanical work is down to the pull. The loop from the magnetic field or power is given by capital B is equal F is equal to B square L square V divided by caps R into V. The P is equal B square L square V square divided by R, equations number 2. When the induced current flow in the loop, Joule heating takes the place. The rate at which is the thermal energy is dissipated in the loop or power dissipated is a P is equal to I squared R. The P is equal to VLV divided by R square into caps R. P is equal to B square L square V square divided by R. This equation is exactly same as the equations P values. Thus the mechanical work done is a moving. The loop appear as the thermal energy in the loop.